So the last couple things I wanted to talk about with gases are standard temperature and pressure, and then partial pressures. So let's start with standard temperature and pressure. Now, usually in research, scientists will agree upon a standard temperature, a standard pressure at which they record their findings. That way it's a bit easier to translate between research groups or across countries, for example, and they can figure out how someone conducted their experiment. So for convenience, scientists selected 273 Kelvin and 1 atmosphere as their standard temperature and pressure, which is also given the abbreviation STP. Now, what's also useful about this, we can plug those values into the ideal gas law. So let's say we've got our PV equals nRT equation. We can plug in that standard pressure, 1 atmosphere, our standard temperature, 273 Kelvin, and then let's assume we have 1 mole of gas. And then we've got our ideal gas law constant, R. So let's solve for the volume. Now, if we rearrange this equation and solve for the volume, we get an answer of 22.4 liters. What's really cool about this is that tells us 1 mole of gas is equal to 22.4 liters at standard temperature and pressure. So this is regardless of the identity of the gas. So it could be hydrogen gas, oxygen gas, helium, nitrogen. It could be any gas. If you have 1 mole of that gas, it will take up 22.4 liters of space at standard temperature and pressure. We can also use this as a conversion factor. For example, let's look at the next slide. Let's say that we have a sample of gas at standard temperature and pressure, STP. So remember, that's 273 Kelvin and 1 atmosphere. And let's say that sample of gas has a volume of 40.5 liters. We want to figure out how many moles of the gas are present in the sample. Well, we already know that at standard temperature and pressure, 1 mole of any gas will take up 22.4 liters of space. So we can use that as a conversion factor. So let's start with what we're given, which is 40.5 liters, and then we'll multiply that by 1 mole and divide it by 22.4 liters. So again, we just use that equality as a conversion factor. So in our calculation, liters will cancel and we're left with moles. So all we have to do is divide 40.5 by 22.4. And that will give us, let's see, 1.8 moles of gas. So by using this equality at standard temperature and pressure, it was very easy to figure out how many moles of gas were in 40.5 liters. So we didn't have to plug everything into the ideal gas law and do extra math. This was a lot easier. So this is a much easier method. But remember, the gas has to be at 273 Kelvin and 1 atmosphere. So you can't use this conversion factor at any temperature and pressure, it has to be those very specific standard temperature and pressure. Okay, one last thing, partial pressures. So what's really cool as well about gases is we can very easily calculate what the pressure of a mixture of gases is. Now, the ideal gas equation can be used with mixtures of gases and pure gases. And there was an English chemist named John Dalton back in the 1800s, and he reasoned that since gases are mostly empty space because they're so far apart from each other, the little molecules, two or more gases are going to essentially behave independently of each other. So let's say you have a mixture of oxygen and nitrogen gas. We don't have to treat this mixture any differently than a pure gas because the oxygen molecules and nitrogen molecules are super far apart. So they act independently of each other anyway. So the contribution that each component of a gaseous mixture makes to the total pressure is known as the partial pressure of that gas. So off to the side, I have a diagram, and on the very far left, there's a sample of hydrogen gas. And there's 0.6 moles of hydrogen gas in that cylinder, and it has a pressure of 2.9 atmospheres. In the middle cylinder, we have a sample of helium. So we have 1.5 moles of helium. And the pressure of this helium gas is 7.2 atmospheres. Now, let's say we take those two containers and we combine them into one container. So we mix those gases together. What we can do to figure out the total pressure of the mixture is just add 2.9 atmospheres and 7.2 atmospheres, and that will give us a total of 10.1 atmospheres for the mixture. So it doesn't matter that we have a mixture of gases. Because they act independently of each other, we can just add the partial pressures together. So the partial pressure of hydrogen, the partial pressure of helium, and get the total pressure of our mixture. So this equation is called Dalton's law of partial pressures. So this tells us that the total pressure of a gas is the sum of the partial pressures of its components. So the other way we can say that, P total is equal to P1 plus P2 plus P3, etc. So these are the partial pressures, the P1, P2, etc. And they're just going to add up together to equal the total pressure of our mixture. So for example, let's say the total pressure of a mixture of oxygen and nitrogen is 1.3 atmospheres. If the partial pressure of oxygen is 0.54 atmospheres, what is the partial pressure of nitrogen? Okay, so let's just write down what we're given. So we're told that the total pressure is 1.3 atmospheres. So that'll be the pressure of the mixture. But we're told that the pressure of just oxygen on its own, so its partial pressure, is 0.54 atmospheres. And we want to figure out what is the pressure of just nitrogen. So again, we're going to use our equation up above. And instead of 1, 2, 3, we're going to use O2 and N2. And then we'll plug in our values. So we've got 1.3 atmospheres for the total pressure, 0.54 atmospheres for the pressure of oxygen. And then we don't know what the pressure of nitrogen is. So now to rearrange this equation and solve for the pressure of nitrogen, we're just going to subtract 0.54 from both sides. So that will cancel on the right. And let's see, the difference between 1.3 and 0.54 atmospheres is 0.76. So that's equal to just the pressure of nitrogen. So that's the partial pressure. So super easy equation to use, much easier than some of the other ones we've seen. But one really good example of Dalton's law of partial pressures is air. So we've mentioned previously air is a mixture of gases. In fact, we have nitrogen, oxygen, carbon dioxide, water vapor, and plenty of other gases as well that are all mixed together in our atmosphere. So when we're breathing in, we're not just breathing in oxygen, right? We utilize oxygen, but there are other gases in the air. Now, nitrogen makes up the largest percentage of air, so it makes up 78% of air. And the partial pressure of nitrogen in air is 594 millimeters of mercury. Oxygen only makes up 21% of the air around us, and its partial pressure is much less. It's 160 millimeters of mercury. But if we add all of these partial pressures together, we get our total pressure, which is 760 millimeters of mercury, which is equal to 1 atmosphere. All right. So in the slides, I did include another law called Henry's law, but I'm not going to test you on this, so you don't have to worry about those or that law in particular. So that's it for Chapter 8. Again, if you have any questions, always feel free to reach out and let me know. And in lab, we'll look at gases a little bit more. So I will see you then.